Hello everyone. This is part 2 of topic 3 and topic 4 for exam 4. This was the page of notes from last time. Topic 3 was telescoping series, and we solved the problem there. And then we looked at the integral test. And regarding the integral test, recall that there's the table of tests for series that's posted in the handouts folder in Blackboard. And this is your cheat sheet for the final exam, and it lists all the different tests that we have, as well as the conditions for convergence or divergence, and I even go so far to give comments as well. Under the integral test, so here was the way we stated it. Continuous positive decreasing had to be proven, and then whatever the integral does, the series will do. And that's basically what this says, just in a different way. It says it could be used for any series. Let the nth term of the series be equal to the function. And you make it a continuous function if the integral converges, the series converges. If the integral diverges, the series diverges. But here's the three things. Continuousness, you can consider Roman numeral 1, positive Roman numeral 2, and decreasing Roman numeral 3. And make sure you know that you need to, and this is for values of x that are greater than or equal to 1. So make sure you realize you have to satisfy these conditions before you can apply the integral test. And that's basically what we did here with our graph. Showed an alternative way to use the first derivative test to show decreasingness, and then we went through and applied the integral test. And basically, if you get a number, it converges. If you get infinity, it diverges. So we'll look at two more examples to finish up this topic. And so I encourage you to use your table with the tests for series as you work through the homework. Okay, so first thing, if you want to get away with, well, you're always just going to say let f of x equal, and then just the nth term of the series, you replace the n by x, so you get 1 over x squared in this case. I'm going to allow you to get away with the graph, remember, to prove the conditions. And the graph of 1 over x squared, we actually saw that earlier when we studied improper integrals. These are basically the same situations as we're going to see. But the graph of 1 over x squared, if we plot a few of the points, let's say when x is 1, 1 over 1 squared would be 1. When x is 2, 1 over 2 squared is 1/4. So it's down here already. When x is 3, it's 1/9. So it's getting to the x-axis pretty quick. Looks like 1 over x, but instead of the first and third quadrants, it's in the first and second. But we are really not concerned about the second quadrant, because we're only concerned with values of x that are greater than or equal to 1. Okay, so then this is the graph of f of x equals 1 over x squared. So, first thing, continuousness. Is it continuous? The answer, yes. So, and that's for x greater than or equal to 1. It is discontinuous at 0, but we're not concerned with that, because again, x greater than or equal to 1. So, is it positive? And the answer to that is yes, by the graph. You could argue these by inspection of the function as well, because you can argue it's discontinuous at 0, so it's continuous for greater than or equal to 1. You can argue it's positive, because no matter what value of x you put in here, 1 over x squared is always going to be positive. But the third thing, the decreasingness, is why you need the graph. And then you can see that for x greater than or equal to 1, it is decreasing. And then I'll show it again. Alternatively, for decreasing this, condition 3, first derivative test from calculus 1. And so the derivative, okay, f of x is 1 over x squared, which we'll rewrite as x to the negative 2, and differentiating, we get negative 2, x to the negative 3, and that's negative 2 over x cubed. And when x is greater than or equal to 1, x cubed is always positive, so negative divided by a positive is negative. So the first derivative is always negative, and if the first derivative is negative, then the function is decreasing. Okay, so again, you could argue, using the graph, you can argue the 3 conditions, or argue the first 2 conditions by inspection, and use the first derivative test to show decreasingness. So once those are satisfied, then you can apply the integral test, and essentially it's just looking at the integral from 1 to infinity of the function, which in our case is the integral from 1 to infinity of 1 over x squared. It's an improper integral because the upper limit of integration, so we should introduce the limit as upper limit's b, so we'll call it b goes to infinity, integral from 1 to b. And actually, let's set this up so that it's integrable at this stage. 1 over x squared, because it's a power in the denominator, we'll bring it up to the numerator as x to the negative 2. And then we can integrate, get this limit out in front, x to the negative 1 over negative 1, evaluated from 1 to b. Okay, before I apply the fundamental theorem of calculus, let's modify the antiderivative. We'll write it as negative 1 over x to the first, or just negative 1 over x. Okay, evaluated from 1 to b. Now, upper limit goes in, so limit b tends toward infinity tagged along. Upper limit, negative 1 over b, minus lower limit of minus 1 over 1. And as b tends toward infinity, by inspection you could say negative 1 over b tends toward 0, because a constant divided by something that's increasing without bound gives you tends toward 0. Or if you want to substitute in infinity for b, we have plus 1 here. And then at that point you realize negative 1 over infinity does tend towards 0, because you take any number divided by a really, really big number, you get a really, really small number. And so this gives us 1. So remember, with regards to convergence or divergence, if we get a number, it converges, and if we get infinity, it diverges. So basically it's saying that the area underneath this graph from 1 to infinity is never going to exceed 1 unit. It's going to converge to 1 unit. Okay, so I'll try to separate this, make it a little more legible. And now we'll finish up with a final example, which is going to be counterintuitive, because it's really similar to the last example, but I think you'll be surprised at the result. So we're going to do the same thing. Let f of x equals 1 over x. Go to the side and graph it. Okay, now the difference between the two, they look the same, 1 over x and 1 over x squared. But the difference between the two is that 1 over x squared drives itself to the x-axis a lot faster than 1 over x does. For example, when x is 1, 1 over x is 1. But when x is 2, 1 over x is just 1/2. As opposed to when x was 2, for 1 over x squared, we were already down to 1/4. And then we went down to 1/9 when x was 3. See, in here we're at 1/2, and then when x is 3, 1/3. And it takes the same shape, that is the graph of 1 over x, takes the same general shape. But as I said, it looks like the 1 over x squared gets to the x-axis a lot quicker. Right, in any event, for x being greater than or equal to 1, there is a portion in the third quadrant here as well, but we're not concerned about that once again because we're only concerned about values of x that are greater than or equal to 1. Okay, the three conditions. Continuous. Okay, yes it is. For x greater than or equal to 1. It's discontinuous at 0. We can see that. Or by inspection. Positive. For greater than or equal to 1. Yes, it is negative over here. But we don't care because, again, greater than or equal to 1. And by inspection, you can see as well. Put x values that are bigger than 1. And decreasing this. And that's the reason why we have the graph, because you can see that it does decrease. And then, once again, I'm going to be formal and say, alternatively, for the third condition of decreasing this, the first derivative test again. So if you're a big fan of the first derivative test from Calculus 1, take the function, 1 over x, we'll modify it, x to the negative 1, differentiate it, get negative 1, x to the negative 2, which is negative 1 over x squared. And now no matter what x is, positive or negative doesn't matter, but x is greater than 1 is what we're talking about. X squared is always positive, negative divided by positive is negative, and if the first derivative is negative, then we've proven that it's decreasing. Okay, so now we apply the integral test. So I'll come up here. So we take a look at the integral from 1 to infinity of the function with respect to x, which is the integral from 1 to infinity of 1 over x with respect to x. Improper integral again, because the infinite limit of integration. So we'll say the limit as b goes to infinity, integral 1 to b. But in this case, we'll leave 1 over x, because it's not a power in the denominator. And we should recognize that, of course, as being the derivative of the natural log of x. So this integrates to be, again, carry the limit, integrates to be natural log absolute value of x, evaluated from 1 to b. Okay, upper limit goes in, so limit as b goes to infinity of natural log absolute value b, minus lower limit goes in, natural log absolute value of 1. Okay, you could take that limit if you want to let b tend toward infinity, or you could just say what it is. Natural log of infinity, essentially infinity, but if you want to write it out literally, natural log of infinity minus the natural log of 1. Okay, but now the natural log of 1 is equal to 0. And the natural log of infinity, if you, I've talked about that in the past as well. You can think of infinity as, or the natural log as like an operator, and it'll shrink numbers, but you really can't shrink the notion of infinity. So the natural log of infinity is really just infinity. But if you want more concretely, graph it. Here's the point 0, 1. I just graphed e to the x. Draw the line y equaling x. And reflect. And that gives you the graph of the natural log of x. And you can see from that as x increases, natural log of x increases without bound as well. So this was kind of a side, just to verify natural log of infinity is infinity. Okay, and there it is. We got infinity. So remember, if you get a number, like we did in the last two examples, we got 1, and we said it converged, we got 1 over e squared or something like that, and we said it converged because they were just numbers. You get infinity, and that's when we use the term diverges. So the counterintuitive thing is the fact that if we're thinking about this as area, the area under the graph of 1 over x from 1 to infinity increases without bound, just tends toward infinity, but the area of 1 over x squared from 1 to infinity never accumulates to be more than 1 square unit. So, kind of interesting. And that is going to lead us to another special type of series, this concept of comparing the 1 over x and the 1 over x squared. So we're going to come back and look at another special type of series and continue our studies. So I'll see you when you are ready.